Hi everyone, my name is Niccolo Zanichelli and I'm here to present a glimpse of a report done in collaboration with Max Jones and Isaac Freeman on the state of brain emulation research. Um, our report focuses on 5 key species: C. elegans, Drosophila, the fruit fly, the larval stage of zebrafish, mice and humans. This is not exhaustive. There are other important models, but these 5 dominate current research. For context, these 5 species span many orders of magnitude in both neuron count and brain size, leading to different levels of behavioral sophistication. From simple movement in C. elegans to elaborate courtship in the fly, the video is not working, to prey capture in larval zebrafish, maze solving in mice, and of course much more in humans. Now, emulation requires matching not just behavior, but internal dynamics as well, typically at least at the level of neural activity. Neural activity can be recorded in various ways, but optical methods today are the most scalable, be they based on calcium or voltage indicators. And for general context, calcium imaging currently enjoys the widest coverage, but generally struggles to capture individual action potentials, while voltage imaging can capture individual spikes, but struggles due to the risk of photo bleaching when it comes to recording session length, limited to a few minutes only. Okay, so in C. elegans, we can record most of the neurons in the C. elegans nervous system, and the focus is increasingly on understanding signal propagation through optogenetic perturbations. In larval zebrafish, the cuticle, which is the exoskeleton, and the tracheal system, which oxygenates the brain, complicate things. Multiphoton imaging systems can bypass the cuticle, but imaging activity in deeper parts of the brain is still made challenging by the scattering caused by the tracheal system. In larval zebrafish, we can record about 70% of the neurons using calcium imaging for up to a few hours, while voltage imaging can capture about 25% of neurons at 200 Hz, but only for a few minutes. In general, whole brain recording is already feasible or could in principle be feasible for C. elegans, Drosophila, and larval zebrafish. Larger mammalian brains, however, face fundamental physical constraints that make whole brain recording unlikely with current technology, meaning that barring completely new technologies, prospective mouse and human emulations will likely have to rely primarily on structural data. So let's briefly review the state of connectomics. In C. elegans, we are now at the stage of mapping multiple individuals to understand connectome development over time. In Drosophila, we recently reconstructed a whole brain from electron microscopy data, and expansion microscopy is getting closer to EM-like resolution using 30 to 40 pair expansion. In larval zebrafish, 2 whole brains have been imaged. One of the 2 datasets, the bench, even includes in vivo functional data from the same individual, but no brain has yet been reconstructed as both datasets still require proofreading. In mice, a cubic millimeter of brain tissue has been imaged using electron microscopy, and there are plans to scale that to 10 cubic millimeters over the next 5 years. In parallel, expansion microscopy is getting closer to self-proofreading technology through protein barcoding, see in particular E11 Bio's work, and to molecular annotation through iterative immunostaining. In parallel still, X-ray imaging has recently achieved the imaging of individual synapses through radiation-resistant resins. Finally, in humans, a single cubic millimeter has recently been mapped using electron microscopy. In general, all major approaches are making progress. EM remains the standard for ultrastructure, but faces challenges in terms of scalability and proofreading requirement. Expansion microscopy is currently the most scalable and cost-effective solution and offers a promising path to self-proofreading technology and molecular annotation. X-ray is the least mature of the 3, but it is also developing rapidly. A brief note about computational modeling. In the past 2 years, we've seen significant progress in some organisms where functional data is available by combining differentiable models with auto-differentiable modeling frameworks with large-scale functional datasets. One example is C. elegans, where we recently saw the BAAI worm emulation of about 130 neurons of the 300 total. For larger organisms where functional data is not available to the same extent, we have seen significant progress by relying primarily on structure. However, it's worth noting that going from an EM connectome to a functional simulation requires making significant assumptions. Xu et al.'s work is worth highlighting and was present in the earlier presentation from Michael as well. In general, we are getting closer to emulations for C. elegans, Drosophila larval zebrafish, and soon larval zebrafish, but mice and especially humans will require a different approach. Humans in particular, due to the sheer size of the human brain, will likely require an industrial approach characterized by large-scale facilities and unprecedented systems integration, from microscopy to modeling on data centers and sample processing facilities and such. And our view is that the capital required will only materialize if the field undergoes a process similar to the process that characterized AI, following the discovery of scaling laws, where increased investment directly correlated with measurably improved model performance. And for this to happen, structure to function, which at the moment is we see as the main bottleneck for successful human emulation, needs to be solved as a bottleneck. There is recent progress. Holler et al.'s paper correlating synapse structure to function is worth highlighting, but not anywhere near as much as we need. And finally, a big thank you to Fieldcrest Foundation and to Foresight and all of our collaborators that made this possible.
Thank you so much. Does anyone have any questions?
In going from scanning a small brain like in a fruit fly up to a human, is the problem the number of neurons and things you have to scan, or does it become a depth problem in getting in and seeing far into the brain?
It depends on. So the question is about what exactly the problem is by going from Drosophila to humans when it comes to successfully emulating a brain. I think the point to make here is that getting functional data in vivo helps a lot when it comes to building a model, be it in terms of validation, but even just for model fitting. Small brains can be recorded pretty much in full, which means that you can get data about every single neuron. In theory, we are not yet capable of it, but at least in principle, we could be getting data about the activity of each and every neuron. For the brain, scattering, so the depth at the moment, makes it limited to about 1.5 millimeters, which is nowhere near enough to actually get activity information about the whole brain, which means that we inevitably have to solve structure to function if we want to someday emulate the human brain.